this exercise again is using the student heights data spreadsheet, and if you click on the normal tab on that spreadsheet, you'll see this. We're investigating here the relationship between standard deviation and the whole distribution. That's the whole of the population or the whole of the sample that you're looking at. In our case, we've been looking at the distribution of size classes and the numbers in each size class, or the frequency within each size class. So in order to do this, then we first of all need to construct a normal distribution. We have the equation for normal distribution, which is written into these cells. You can recognize it. It's got pi in there and an exponential function, and the parameters that are being used in the equation are the mean and the standard deviation. I'm going to define the shape of it. So that's copied down, and we've got height classes, notionally height, it could be any other parameter in the leftmost column, and we've set those at 0.02 apart, only because it means that we end up with 100 cells filled, which is something that you can see on a single view of a spreadsheet. You'll see as we go further on that ideally we'd like to have it several thousand cells long, but it's just a bit awkward for us to deal with that in that way, and we're only using it to illustrate a point. So these parameters then in the top left, the mean, the standard deviation, and the class size. If we change the standard deviation, so if we put in 0.1, which yours may be already, you can see the shape of the distribution changes. Because we've fixed the population size, in this case we've fixed it as 1, then the area under the curve is always going to be equal to 1. And so if the distribution narrows, because we made a smaller standard deviation, then it must grow taller. So you can see if we change between 0.1 and 0.16, distribution flattens for 0.016, spreads out, and also it drops, so it's not 4.5 at the mean anymore, it's 2.5. So you can have a play around with that anyway, just to get used to the normal distribution. But if we return that to 0.1, the thing that we're trying to establish then is the relationship between standard deviation and the area under the curve, the whole of the distribution. So what I want you to do is to fill in these three columns with the area of this distribution that lie within 1 standard deviation, 2 standard deviations, and 3 standard deviations of the mean. What's written in here is the area under the whole distribution, so all of the area under the distribution. And you can see that's calculated by multiplying the size class, which is the x dimension, multiplied by the frequency, which is the y. So you're just getting the area of a small rectangle under each of these points, multiplying the x, which is the size class, by the y, and that gives you the area. So you can see that. It's an absolute reference to the size class because it stays the same. So it's always referring to that cell. And that cell also is used to draw the size classes because it's just the increment between each of these cells, constantly adding 0.02. So that's how we worked out the frequency. That's how we worked out the area, which is multiplying the x by the y being the frequency, and the y has been determined by using the equation for the normal distribution. So the area that lies within 1 standard deviation of the mean, well, the mean is 0.5. We can just put that in bold so it stands out. And standard deviation is 0.1, so minus 1 standard deviation is 0.4. So the area is that, and we need to add together the areas from 0.4 through to plus 1 standard deviation, which is 0.5 plus 0.1, which is 0.6. So all those numbers, and if we put in a formula up here just to sum them. You can sum those numbers. The only numbers that are present are these. We can copy that to these ones as well. You can see that the area that's been worked out for the total area is equal to the sum of all of these. So it's been divided by B1, which is the size of the population. So in this case we've made 1. If you made it 500, this would still evaluate to 1 because these areas have increased, so they'll add up to 500, and then you're dividing by 500, B1. Okay. Put that back to 1. Because by having it as 1, it allows us to quote these numbers as percent. So within one standard deviation of the mean, it's 0.72 of the, or actually close to 0.73 of the total area being 1, so 70, just over 70%. Then if we go to 2 standard deviations of the mean, and 0.5 minus 2 standard deviations, which is minus 0.2, so that's 0.3. So that's the area, and taking that down past the mean to plus 2 standard deviations on top of the mean, 0.7, and then we get 96, just over 96%, and then finally 3 standard deviations of the mean, 0.5 minus 0.3, so it's 0.2. Area. Plus 0.5 plus 0.3 is 0.8. Okay. So within one standard deviation of the mean, imagine there's the mean, one standard deviation, this area just over 70%. 2 standard deviations of the mean, just over 96%. And that's the figure that you should recognise. We've talked about the confidence level that we normally work at, which is 95%, and it's been noted, and you'll have come across it several times already in your careers, that 1.96 standard deviations covers 95% of the distribution. So 1.96, which is known as the D value, if you have a D value of 2, instead of 95%, you've got 96, so a bit more. So you can see that if you've got the standard deviation, if you've got 1.95 times the standard deviation, it'd be here, 1.9, and 2 times standard deviation, it'd be a bit further, so you'd cover a bit more of the distribution, 96%. And at 3 standard deviations, we've mentioned this before, and we've talked about people that may be, or places or things that may be 3 sigma weird, 3 standard deviations weird. That is because they lie outside of the 99.8% of the population. So that's covering 99.8 or more percent of the distribution lies within 3 standard deviations of the mean, so all the way out here, and you're very much in the tails of the distribution. So there's a number there you might recognise. These numbers aren't exactly correct, and that's because of the resolution here. These classes, we've only got 100 classes. If we had 1,000, then these would be closer to the actual values that you'd find in a statistical textbook. Another thing that you need to assure yourselves of is that if you change the standard deviation, then these values stay the same. So let's just do that. If we change it from 0.1 to 0.16, straight away you see the distribution flattens out, so it gets wider, therefore it must drop because the area under the curve stayed the same. Area under the curve is still 1, so it stayed the same. And we need to adjust these numbers now. So instead of just being 0.5 minus 1, it's 0.5 minus 1.6, so minus 0.16. So we need to extend this, another 1, 2, 3. We need to extend this, another 1, 2, 3. Okay, and we get effectively the same number, just over 70%. Here we need to extend this by 1, 2, 3, 4, 5, 6 to 0.18. So that's 0.5 minus 0.16 twice, which is 0.32. And similarly in this direction as well. 1, 2, 3, 4, 5, 6 cells more. So from 0.82 to 0.18, and again 96%. It's not exactly the same, but that's just because of this lack of resolution here. And then 3 standard deviations is going to be 0.48, so that's 0.5 minus 0.48, which takes us down to 0.02, and 0.5 plus 0.48, which takes us down to 0.98. And again 99.78, 99.8, so the same numbers. So those standard deviations changed. The relationship between the standard deviation and the area under the curve, or the whole distribution, or the population, or the sample that you're dealing with, remains the same. And that's what we want to be assured of. And that's why we can use these numbers, the numbers of standard deviation, which are known as the d-values. We can use them in order to work out probabilities, which are these numbers.